Have you ever wondered what a perfect prediction would look like? And I don't mean just, really good. I'm talking about something that is mathematically, provably perfect. Well, it turns out a model like that actually exists in the world of AI. It's the unbeatable gold standard. But, and there's always a but, right? You can't actually use it. Okay, let's dive into this incredible story of the perfect AI that's always just out of reach.
So it really all boils down to this one big question. You see, in machine learning, a lot of what we do is about classifying things. Is this email spam or is it legit? Is this customer going to buy something or not? The goal is always to create a model that makes the right call as often as possible. But what's the absolute best it could ever do?
So take a look at this. It looks pretty simple, right? We've got a bunch of green dots and a bunch of red dots, and our job is to draw a line that separates them. I mean, you could draw a straight line down the middle, maybe you get a little fancy with a curve, but which one of those is truly the best one, the optimal one? This little picture right here, it's the core challenge data scientists face every single day.
Well, to answer that question, scientists came up with this theoretical model. And it's not just another algorithm. Oh no, this is the ultimate benchmark, the hero of our story, if you will, the Bayes optimal classifier. It promises to make the most probable and therefore the best prediction every single time. So what's its secret? Well, it's just the sheer ambition of the idea. Instead of just trying to find one single best line to draw between those dots, the Bayes optimal classifier does something kind of crazy. It considers every single possible way you could draw it, all of them. And then it combines all those predictions, giving more weight to the ones that are more likely to be right. It's like the ultimate democratic vote, but for data.
And look, this isn't just someone's opinion. This is a cold, hard, mathematical fact. If you give it the same information, no other model can beat it. On average, it is perfect. It is, quite literally, the highest score you can possibly get.
And that's why we call it the unattainable gold standard. It's this perfect ideal that everyone in the field is kind of chasing. Think of it like Mount Everest for machine learning. We all know it's the highest peak, even if we can never actually get to the top.
But that word right there, unattainable, that's the key to this whole thing. I mean, if this model is so perfect, why aren't we all using it? Well, this is where the story gets really interesting. Perfection, it turns out, comes at a price. A really, really big one.
So that's the big question, isn't it? Why would you even create a gold standard if you know nobody can actually use it? The answer isn't in the theory. It's in the messy, brutal reality of just how many calculations are involved. This massive problem has a pretty cool, dramatic name, the curse of dimensionality. And what that basically means is that every time you add another piece of information, another feature for the model to think about, the number of calculations you have to do just explodes. And not in a straight line either. It grows exponentially.
Okay, let's put some numbers to this to see how crazy it gets. Let's say we're working with just 10 simple yes or no features. You'd need to estimate around 2,000 parameters. Okay, that's doable, right? We can handle that. Now let's bump it up to 20 features. Boom! All of a sudden, you're at over 2 million parameters. And what about just 30 features?
Get ready for this. You'd have to estimate over 3 billion parameters. 3 billion. To do that right, you'd need a data set so massive, it would have to show you every single one of those billions of possibilities, probably multiple times. It's not going to happen. It's computationally impossible.
Okay, so perfect is off the table. It's impossible. But what if there was a shortcut, a really clever, kind of sneaky way to get most of the benefits without the impossible workload? Well, enter the pragmatic hero of our story, the naive Bayes classifier.
Now, naive Bayes gets its power and, yeah, its name from one giant simplifying assumption. And let's be clear, this assumption is almost always technically wrong, but it's what makes the whole problem solvable.
So what is this big shortcut? It's called the naive assumption of conditional independence. What that means, in plain English, is that the model pretends every single feature is completely independent of all the others. It treats every piece of evidence like it exists in its own little bubble.
And you can really see the difference between the two approaches here. The perfect model, the Bayes optimal, is trying to map out this incredibly complex spiderweb of how every feature interacts with every other feature. But naive Bayes, it just takes a pair of scissors and cuts all those connecting threads. It just says, nope, I'm going to look at each piece of evidence by itself. Thank you very much.
Okay, here's a really good way to think about this. We all know that thunder and rain are related, right? They go together. But let's say you already know for a fact that there's lightning. Does knowing that it's also raining give you any new information about whether you'll hear thunder?
Not really. The lightning is the main event. Naive Bayes basically takes that exact same shortcut logic and just applies it to everything, all the time.
And that really brings us to the big takeaway here. What we have is this classic showdown, the ideal versus the real, the perfect theory versus what actually works. And honestly, it teaches us a ton about how AI gets built in the real world. So let's just lay it all out. The Bayes optimal classifier, its goal is the absolute most probable prediction. It does this by combining everything, but it's totally impossible to actually compute. On the flip side, you've got naive Bayes. Its goal, a prediction that's fast and good enough. It gets there by assuming everything's independent. And while it's technically naive, it's super useful for real-world stuff like classifying text.
So, if there's one thing to remember from all this, it's this. Making progress in machine learning isn't always about chasing theoretical perfection. A lot of the time, the real breakthroughs come from finding these clever, elegant shortcuts that make impossible problems possible.
Now, you'd think that making an assumption that's almost always wrong would make the model terrible, right? But what's so amazing is that it's surprisingly effective. As this quote says, the model is robust enough to basically ignore its own flaws. Even though the underlying logic has these serious deficiencies, the final result can still be incredibly accurate.
And that leaves us with one final big question to chew on. In this whole world of AI, is it possible that the relentless pursuit of perfection is sometimes the enemy of actual progress? Maybe, just maybe, being a little bit naive is exactly what we need to get things done.